So hello everyone, today we are going to learn about heat pump and refrigeration. So it is a practical on heat pump and refrigeration. So in this practical we have to understand the working principles of vapor compression refrigeration cycle, and as well as we need to determine the COP or coefficient of performance of the cycle. So the apparatus required are, or the equipments we need are, air and water heat pump, vapor expansion thermometer. So the theories are compressor. So compressor is simply a device or simply a thing that consumes mechanical work which increase the pressure of the fluid. And moving on to next, we have refrigeration. Refrigeration is a thermodynamic cycle which removes heat from a lower temperature, that is object refrigeration, and rejects at a higher temperature. So expansion valve, it reduces pressure of the fluid without consuming work. We know that. And evaporator, it is used to evaporate a liquid by taking heat. And condenser, it condenses vapor to the liquid by rejecting heat. So these two are the figures or the graph between pH, that is pressure and enthalpy, and pressure and entropy. So this is the saturation curve. From 1 to 2, that is isentropic compression. We stay from 1 to 2 process is isentropic compression. In isentropic compression, while plotting the graph between P and S, that is pressure and enthalpy, it just goes out to superheated region, right? And next, and in the case of T and S, that is temperature and entropy, it just goes above the superheated line, and then superheated temperature line, and then the step or the process 2 to 3 is known as isobaric condensation. In isobaric condensation, it goes into, that is inside the saturation curve, that is it is in two phase, right? It is in two phase. And same, that is in the case of TNS, it first decreases, that is it enters into saturated gas. Yes, saturated gas, it enters into saturated gas, and then it also goes to two phase, right? Now moving on to next, we have, that is 3-4 is isenthalpic compression. In isenthalpic compression, it decreases from 3 to 4, that is enthalpy is constant, and 4 to 1 process is known as isobaric evaporation. Goes here, and you can see the graph. So to be more clear, I'm going to show you the theory of this practical. So if we understand this, it will be more clear to us. So the experiment or the topic is vapor compression refrigeration cycle. So I said earlier that the process 1 to 2 is isentropic compressor. So in isentropic compressor, saturated vapor from the evaporation, is compressed isotropically in compressor. During this process, obviously pressure increases, enthalpy increases, temperature increases, but entropy is constant, right? Entropy is constant. So I guess you guys can draw this PVPH and PS diagram or curve. And moving on to next, we have isobaric condensation. So high pressure, high temperature, superheated vapor. Yes, from this process, that is when you just take saturated vapor from evaporator, it is compressed isotropically in compression, right? So at this process, the saturated vapor is converted into superheated vapor. So high pressure, high temperature, superheated vapor enters into condenser. It condenses to a saturated liquid by losing heat at constant pressure, right? So first process is at evaporation. Saturated liquid from evaporator is compressed, and it is converted into superheated liquid, that is at high pressure and high temperature. The superheated liquid is again passed to condenser, and in that process, that superheated liquid is converted into saturated liquid, losing heat and at a constant pressure. So in this process, we should know that pressure is constant, temperature decreases, enthalpy decreases, entropy also decreases. Now 3 to 4 process is isobaric expansion, so it must expand, right? So high pressure high pressure saturated liquid. High pressure saturated liquid enters the expansion valve where it expands at constant enthalpy. So when it enters, so expansion valve is a device which increases pressure, but it does not have any effect on the work, right? So at this process, pressure decreases, temperature also decreases, enthalpy is constant, and entropy increases. So when that saturated liquid is again passed again enters into expansion valve, at that time it expands at a constant enthalpy, right? So at the process, the pressure decreases, temperature decreases, enthalpy is constant, but entropy increases. And the final process, or the final step in this process, is that isobaric evaporation. In isobaric evaporation, isobaric, we know that pressure is constant, isobaric pressure constant. So refrigerant after expansion enters into evaporation, where it receives heat and evaporates at constant pressure. During this process, pressure is constant, temperature is constant, in enthalpy increases, and entropy also increases. This first you need to you need to have this concept, you need to have this figure in your mind. First step is isobatic compression, from evaporation to compressor. Second is isobaric condensation, from compressor to condenser. Step 3 is isenthalpic expansion. Isenthalpic expansion is from condenser to expansion valve. And finally we have isobaric evaporation, is that is from expansion valve to evaporation. So these are the things you need to have in your mind. Now moving forward, we have the, so what is heat exchanger? Heat exchanger exchanges heat between two fluids, right? This is the same figure as I have shown you earlier, that heat pump and refrigeration cycle. Now moving on to next, we have procedure. First thing is we need to turn on the water supply to the unit and turn on the main switch. We need to note down the water inlet temperature at first. Select the air evaporation by pressure the evaporator. Change over the switch down. Allow the unit time for all the system parameters to reach a stable condition, and fill up the observation sheet. The exchange over switch up condition, and fill up the observation sheet. So calculate COP for both water and air heat pump, right? So calculation and observation, I guess you guys can just do it in your own project, in your own lab. So first thing is for water evaporation. At that time we need to know that compressor electric power, if we have to supply the electric power, suppose we have supplied 180 watts, and water inlet temperature is T1, that is 12 degrees centigrade, and water outlet temperature is T2, that is 10 degrees centigrade. So these are the things that we need to calculate by ourselves. We need to have the device, and that's all. Now moving on to next, we have condenser water mass flow rate. Mass flow rate is divided by time, so it is should be in kg kilogram per second, right? So, or you can say that m dot also can be written for mass flow rate, and that is for condenser. Now moving on to next, we have to calculate the QL. QL equals to mcp, because we are calculating it at constant pressure, because isobaric, right? So mcp t2 minus t1 minus t2, from step 1 to from 1 to 2, right? That is isentropic compression process. So we have to calculate these values, and we see Pw is the specific heat capacity of water, and we also need to determine the COP, also known as coefficient of performance, right? That is QL, that is heat supplied at the lower temperature, or the QL, and divided by total work done. We have calculated that from earlier, right here. QL we need to calculate, that is 180 watt, is given directly by the supply electric power, and in this way we can calculate the value of COP. Moving on to next, we have is for air heat pump. That's same, we need to just repeat the same process, right? Compressor electric pressure input, W, that is watt, 180 watt. The work is equals to not watt, work is equals to 180 watt. Water inlet temperature T1 and water outlet temperature T2. Condenser mass flow rate MC, same. Then Q equals to M CP, the CPW T1 minus T2, same. Then we need to calculate the COP. In this way we can observe the result. So result is simply the coefficient of temperature, COP, of the water evaporation air heat pump was found to be 1.48 and 3.488 respectively. So in this way we can conclude the experiment. Thank you very much.